So the class that we're going to focus most of our attention on is the dividing line between polynomial and non-polynomial algorithms, which to us kind of means the difference between polynomial algorithms and exponential algorithms. But anyway, here's an example of a graph problem. This is famously known as the traveling salesman problem. And it's basically saying you're given a map with a set of cities, like the United States, for example, and you're given a set of cities, and each of the cities has a distance between them, and you want to visit every city. And you want to do that by walking around to all the cities, or go by car or whatever, with the shortest distance, your total shortest distance, and yet you have to visit every city. Okay. So one example of one algorithm to solve this would be to try every combination. In other words, list out all the cities in every order that can be, every permutation of all the cities, and then ask yourself, how long does that path take? And then how long, try that for every city, and then take the one with the shortest path. So if we were to compute that, if there was one city, it would take one step. If there were 5 cities, it would be 5 times 4 times 3 times 2 times 1. That would be 120. There'd be 120 possible ways you could visit 5 cities in different orders, starting and stopping. If there were 10 cities, this algorithm would be a little over 3 million steps. 15 cities, it would be 1.3 times 10 to the 12 steps, and 20 cities, it would be 2.4 times 10 to the 18 steps to do this. So, if we were to use that, let's say the n is 20, suppose we had a processor that can determine a path, calculate its length, and save it if it is less than the best answer we have so far. Suppose it was able to do that all in 1 gigahertz, right? Now that's actually a lot of work. I'm actually trying to do one computation. Okay, so let's say it was able to do all of that in 1 gigahertz, which is very unrealistic today because processors coming out at 3 gigahertz. How much, has anyone bought a computer recently? Are they about 3 or 4 gigahertz now, the processors? Okay, so I think I wrote this up like a year or 2 ago. So anyway, if we were to use the processors that are coming out today to solve this traveling salesman problem, and we wanted to evaluate 2.4 times 10 to the 18, if we divided it by the speed of the processor, which will tell us how many seconds it would take, then divided that by seconds, 60 seconds, 60 minutes, 24 hours, 365 days, this algorithm would take 76 years to compute if we used n as 20. So again, this is an exponential algorithm because we're taking n permutations, but just to give you an idea, with 20 cities and the processors that you can buy now, like down in Staples when you buy a pretty good computer now, with n being 20, using an exponential algorithm, it would take 76 years to run. And I'm also making the assumption that we can compute the entire length of the path in one instruction, which is not even true. We'd have to hop through all 20 instructions and add them together. It would probably take about 40 instructions just to compute one path. So probably for n's of even 15, it would probably take more than a lifetime to solve the problem. Okay, so that's just some kind of food for thought for that particular algorithm. So hopefully we would then want to use a better algorithm than an exponential algorithm. We never want to use a computer to run an exponential algorithm on it, because once n gets somewhere in the 15 or 20 zone, we'll never see the answer to the problem. Okay, so then just a couple of 2 definitions, completeness and hardness. For any class, linear, n log n, polynomial time, for any class, a class is said to be, whatever the class is, hard, if the most efficient algorithm of all the algorithms in the world is as difficult or more difficult than, for the problem C, I'm sorry, a problem is a particular class hyphen hard if the most efficient algorithm is as difficult as all the problems in that class or even harder. So to say that a problem is, for example, linear hard, and you might see it as L hard, that means that problem is as difficult or more difficult than any of the problems that can be solved in linear time. And then the idea of completeness is for a problem that is a class complete, that means the problem is, for class C, if it is both in the class and is as hard or harder than any other problem in that class. So it's kind of a formal definition saying that if a problem is some class complete, it takes the best algorithm in the world to solve that problem takes a minimum of whatever the class is. And this one is saying you might not, this one will come up very rarely in our algorithms class, but comes up a little more often in theory classes. These are problems that may not even be in the class, but they are at least as difficult or more difficult than the class. So for example, to use this concept of hard in a sentence, we could say that sorting, which we know is n log n, is linear hard, meaning it is as hard as any linear problem, and who knows, it might even be harder than that. That's really what we're saying. So, but the complete one will come up a little more often. So, then the definition of polynomial time algorithms are a class of all problems that can be solved with an algorithm that has a polynomial running time. Theoretically, P is the class of all problems that can be solved recursively on a deterministic Turing machine. And a Turing machine is a model for a computer program. Okay, non-deterministic polynomial time. An NP complete problem is a problem that is in the class NP and is as hard as any other class, any other problem in the class of NP. So a non-deterministic polynomial time algorithm problem is a problem that if I gave you an answer, you can in polynomial time check that it's a valid answer. It makes sense that this would be as difficult or more difficult than all the polynomial problems because we could enumerate all of the answers and then try them out in polynomial time. So we can obviously solve anything we can solve non-deterministically in polynomial time, we could solve in polynomial time. And then it is a subset or possibly equivalent to all the exponential problems because there are at most exponential possible inputs that we would have to test. So if we can come up with a polynomial algorithm to verify that an answer is legitimate or not, we can run that on all exponential algorithms and then we'd have the best answer. So any problem where you could verify an answer in polynomial time, you can verify every possible input in exponential time because there's n factorial inputs and you'd have to run this polynomial time algorithm on the n factorial inputs. So the running time of something that tries every input and checks whether it's a good answer or not would be n factorial times a polynomial, which is exponential. Okay, so the goal of this problem, this was the person who kind of came up with this idea of this NP completeness topic in the 1970s, wanted to invent a problem that will be polynomial complete, meaning it's harder than a linear problem, it's harder than an n log n problem. It's a problem that will take a minimum of n to some k, n to a constant, like 3 or 4. It's not just like n log n, it's going to take a minimum of n to the k. So the problem was this. I don't know if you've seen hardware circuits before where you can, where you put gates together and like this. You have inputs, which are zeros and ones. And you take these inputs and you wire them together into a circuit, an AND gate, and these two might run in together into an OR gate, and then these two outputs might run into an AND gate, and so on. You've seen circuits like this. So all we're doing is saying if this or this is a 1, then the result is a 1, or they can be ANDed together, and then this can go on and on. We can actually build a very, very large circuit, and eventually at the end, one bit comes out, and it's either a 0 or a 1. But this thing could be, if you think about it, this is our input. It's our zeros and ones. The circuit can actually get wider, can be more than that, right? Because we can have really as many combinations as we want. Now you might think it could go infinitely wide, but it can't because it has to eventually resolve to some number. But the question is, what the inventor of this question, he was trying to come up with a question that is going to take at a minimum polynomial time. Nobody will ever come along with a better algorithm that can run in a better class than polynomial time. So the goal was to come up with a problem that is P, polynomial complete. Meaning, he'll present an algorithm that takes polynomial time to run, and he's also going to make the statement that nobody will ever come up with an algorithm that is more efficient in a lower class than P. And P, if you remember, is n to some constant, like let's say C or K. So this is a polynomial time algorithm. Runs something like that. Exponential, if you remember, is C to the n. So I wanted to come up with a problem that is P complete, polynomial time complete. So based on the size of the input, we keep doing passes. We evaluate combinations, and then those feed into another layer, which feeds into another layer, and eventually comes down to a final answer. But this is how wide can these work layers go? And they could be multiples of n. And there's no real cap to these either. If we have 50 layers, if the first layer has 50 gates coming out of it, those 50 gates could create another 100 gates in the next layer. So we could code the input to be something like, we could use symbols like greater than, less than 0, or 1, and 1 or 0, and we could code it up this way instead of coding it as pictures of a circuit. We could code up the input this way. And obviously the program, or theoretically a Turing machine, has to keep reading these symbols and then evaluating, collapse this into a 0 or a 1. And it does that after one pass, and then another pass comes back, and eventually it keeps doing passes and passes until it finally gets to the final answer. But the question is, obviously one way to solve this is a polynomial time algorithm. Let it run on multiples of n to some constant, running back and forth, and we really don't have any control until we're done. Then the argument is there any other more efficient way to solve this? And just for today's purposes, can anyone think of a way? I mean, the argument is there is nothing other than evaluating at each pass to come up with an algorithm. If you try to do something like, let's say we had a 0 got wired into an AND gate down here, we might be able to say there's no point in evaluating this whole thing because the 0 will cancel it out. So now we're looking for like shortcuts or some better algorithm. But if this input could be a 1. So we could have an algorithm that says anything down at this level that's wired into an AND gate, if it's connected to a 0, we can skip something. But we can't be guaranteed that it'll always skip something. So in the end, any algorithm to solve this question, which they call what is the circuit's value? Its value is either a 0 or a 1. Any algorithm that would solve this question has to run at a minimum polynomial time, and n raised to the power of k. So this ended up being the world's first polynomial complete problem. So if we believe that this is a polynomial complete problem, there'll never be a problem that runs quicker than that. Then another interesting question becomes, instead of the question like we just had before, where you're given the zeros or the ones, instead, suppose you were just given the circuit, and you're asked the question, is there any input, any combination of zeros or ones where the circuit will be satisfied, meaning a 1 will come out. So there could be circuits that are not satisfiable. Maybe, let me go over an example of a circuit that's not satisfiable. So we'll know, let's get an idea of the question that's being asked. What's an example of a circuit that's not satisfiable? So a circuit like, let's see, go from the bottom. An AND gate, and we could use NOT gates too. Oh, actually I can think of an easy example. We have 2 inputs, and both of these are zeros. Okay, so what I'm saying is it possible that they can both be zeros, both be ones, one be a 0, one be a 1, and the first one be a 0, and the second one be a 1? Is there any combination of inputs you can put here that would make, and I'll run all of these into a big OR gate. Is there any, oh no, not an OR gate, an AND gate, or another big AND gate. Is there any way you could set these, say X and Y, so that a 1 will come out? It'll never happen. So as you can see, some circuits are satisfiable and some are not. This is an example of one that's not, obviously one that is. Many examples of one that is. You could just say, we could have a 2-input gate like that. Is this satisfiable? Yeah, if you put 1s on each end, then you'll get an answer. It'll end up being satisfiable. So if we were to ask the question, phrase the question a little bit differently and say, is this circuit satisfiable? So this is a more vague question. This is the first question, the circuit value one, was we would give you a circuit and the inputs, and you would have to tell me, is it a 0 or a 1? Here you're just given the circuit and saying, is there any input that could make it come out a 1? So this is called the circuit satisfiability problem. Well, one way you can solve this is to try every combination of inputs and then check. Run the algorithm on the previous problem, which we decided we can do in polynomial time. So this one solution to this is to run the n factorial possible inputs and then check the answer in polynomial time using the solution of the previous problem. That's one way to solve it. The big argument that this guy, I think his name was Cook, made in 1991 is that's the only way to solve this problem. There is no other solution to this problem. The only way to solve it would be to try every possible input and then take every possible input there is and then check if that works. So we might try to come up with an improvement of like a pruning algorithm where, let's say we tried all zeros and we realized that doesn't work. And if a 0 is in the first bit, that would kill the whole circuit, so we don't have to do any other combinations as long as the first one is 0. We could start making it a little bit quicker, but it would still end up taking n factorial to solve this problem. So the argument he made was this is a problem that takes a minimum of exponential time. And then other computer scientists who read this paper was saying, well, this problem can be, this is a class called, not not a problem in the class of exponential problems, but it's a problem in the class of non-deterministic polynomial time problems, meaning if I give you an answer, you can check it in polynomial time, which a lot of people argue that is the same thing as being exponential. And some people say, no, I think it's a subclass of exponential. And to this day, it's not proven yet whether it is a subclass or not. So they decided to call this class the non-deterministic polynomial time problems. And it ended up being, I think his original intention was to say that circuit satisfiability. If I give you a circuit, can you tell me is there any set of inputs that will satisfy it? I think his original goal was to say that this problem is exponential complete. And therefore saying the only algorithm you'll ever use to solve this is an exponential running time algorithm. But a lot of other critics or whatever was saying, well, the one thing we know about the class of problems is that if I gave you an answer, you can check it in exponential time. So we'll call it the non-deterministic polynomial time problems. And we'll keep in mind that that might be exactly the same thing as the exponential problems. Or the NP class might be a subset of the exponential problems. In other words, there might be problems in the NP class, there might be problems in the exponential class that are not in the NP class, but no one's found an example yet. So, non-deterministic problems are basically a problem where you take a guess at an input, and then you can check in polynomial time whether the input is valid or not. So if somebody gave you a set of zeros and ones, you could run the circuit value algorithm, which we know can be done in polynomial time. In fact, we know it's polynomial complete. And then we can answer yes or no, did that work? And then if we want to, we can run that algorithm n factorial times and solve the problem. So then just some examples of just using completeness in a sentence. For example, find max is considered a linear complete problem. Not only does it take a minimum of linear time, but nobody will ever find an algorithm that does less work than linear time to solve it. Sorting, we know, we saw a proof earlier, that comparison sorting, where you don't know anything about the inputs, it's not like from 0, the values are from 0 to 100. If you don't know any information, the only thing you can do is compare numbers. Every value has to be compared against at least log n other values before we can put it in its final spot. So sorting is considered an n log n complete problem. So there's an algorithm that runs n log n, and that nobody will ever come up with an algorithm better than n log n to solve sorting. And then, like we just talked about before, the circuit value problem, where you're given a circuit and the inputs, the zeros and ones, to check, to determine whether the output of the circuit is a 0 or a 1. That is a polynomial complete problem. And then the question where you're not given the inputs and you're asked, can you find any set of inputs that will satisfy the circuit? That is now this new class called NP complete, meaning, and if you think of this as exponential complete, it kind of makes more sense. It's as hard as any exponential algorithm, and nobody will ever find an algorithm more efficient than that. So we can, okay, so if you believe, now that this is like, that statement that the circuit satisfiability problem is NP complete, that's a huge statement. We could spend like probably 2 hours going over why that ends up being true. But now, just assuming like that we agree with that, here's a problem that looks like it should be an easier problem or possibly as difficult as the circuit satisfiability problem. So this is a problem where the circuit satisfiability problem is a problem where you could get inputs that say the first 8 inputs get ORed together, and then that result gets ANDed with something else. So the gates can be of any size. They can take as many inputs as you want, and they always produce one output, and then those run into any other kinds of gates. If we had a problem where every gate has exactly 3 inputs, and every gate has to be in conjunctive normal form. Conjunctive normal form means every gate is an OR gate, and then when the results of the OR gates always get ANDed together. So this is a very small subset of circuits. All the circuits can only have 3 inputs, and the gates can only be OR gates, and then their results get ANDed together. So this looks like it should be an easier problem than the original one, right? Because it's very limited in what the input could do. So does it seem like this one might be solvable in something better than exponential time or NP being in the NP class? Have we made it restricted enough that it could make things better for us? Okay, so anyway, what we can actually do, it turns out that having this restriction does not make it solvable in something better like polynomial time. The reason is we could take any input that has one literal. Like in the original problem, you could have a gate that has 1 input, 2 inputs, 3 inputs, could go up to 50 inputs. If we had one literal, we could force it into, if we had one literal, we can force it into a 3 conjunctive normal form input by saying A plus 2 values, we'll just make up 2 brand new values, x1 and x2, A or x1 and not x2, A or not x1 and x2, and A or not x1 and not x2. And now we have the freedom to do whatever we want with x1 and x2. We can set them any way we want, and if A is a 1, this thing has to turn into a 1, no matter what x1 and x2 are. And if A is a 0, the 0 for A will zero out all of these, and the value will be 0. So this expression, this long expression right here, is equivalent to saying A. Does that make sense? I know it's a little strange saying this the first time. If you have an input called A, if it's a 1, it's a 1. If it's a 0, it's a 0. But now, let's say I want to impose this new rule that the circuits, the input to the problem, have to be done, every gate must be a 3 input, there's a reason for doing this later on. Every input must be a 3 input OR gate, and then every OR gate has to be ANDed together at the end. So suppose in your original circuit satisfiability question you had a gate that just, it's not even a gate, it's just a literal. That's an input value. If it's a 1, then this equivalent version will be a 1. If A is 1, then no matter what we do with x1 and x2, this one of the 4 will definitely be on. And then when we add them together, it will be equivalent to the A being on. So case 2 is when we have 2 literals. Let's say we have an A and a B. We could say the 3 conjunctive normal form equivalent to this is A or B or x1 and A or B or x2, the not of x1. So no matter what the value of x1 is, one of these 2 terms is going to be A or B. So for example, if x1 is a 1, this will be a 1, and then this term will be a 1, and the other term will be whatever A and B is. So these 2 ANDed together will be whatever A and B is. So this piece right here is exactly the same as saying this piece. So for example, if A or B is true, then both of these will have to be true. One will be A and B, and the other one will be 1. So all we're doing in this case is basically saying this. We're taking the original problem, which is our first NP complete problem, and coming up with a restricted version of it, because this is going to help us map into other problems, where we're saying the input, it's a circuit, but the input has to be 3 things OR together, 3 things OR together, 3 things OR together, and then whatever the results are get ANDed together. So this is a much restricted version of the previous problem, but we're going to find out it's just as hard to solve. If you had a gate in your original problem that had 3 inputs, we write that exactly as it is. And if we have more than 3 inputs, let's say for example, we had 5 inputs, 1, 2, 3, 4, 5, I'm sorry, 1, 2, 3, 4, 5, 6 inputs. We could do the equivalent conjunctive normal form by saying we have A, B, and x1, and then the not of x1, C, and 2, and the not of x2, D, and x3, the not of x3, and then E and F. Whatever values we assign to x1, x2, x3, x4, this piece here will take on the same value of this. So basically, if any one of these is a 1, A, B, C, D, E, or F, if any one of these is a 1, this whole circuit would be a 1. If we put a 1 anywhere here, this will be satisfiable. We would be able to play around with the x1s, these things that link them together by saying, let's say for example, the B is a 1. So we have a 0 and a 1. We could let this one be a 0, which makes this one a 1. And then that'll make this whole circuit 1. We could let this one be a 0, which could make this one a 1. And let this one be a 0 and make this one a 1. So we can make all of these turn 1 by playing around with the x1 and the x2s. As long as one of these is true, we could figure out a way to make this true. If all of these are false, then there's no way we could play around with the x1, x2, x3 to make this work. If this is false, false, that forces this to be true, which forces this to be false. This being false, this has to be true, which makes this false. This has to be true, which makes this false, and now this being false, 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 this would be stuck at false, and they all get ANDed together. So basically, the original problem, which sounded like, the circuit satisfiability one, that seemed like a hard one. This one, we thought we may have restricted it down to the point where it became easier, but the truth is, we could take any input of the original problem, run it through these steps, and now we have the new 3 conjunctive normal form SAT problem. And if somebody came along with a solution for this problem, they've solved the other problem. Because, right, that was the whole point of that reduction stuff. If someone could come up with a way to solve the 3 conjunctive normal form problem in, let's say, polynomial time, then you found out a way to solve the original problem in polynomial time. Step 1, you would convert the input following these rules to this problem's input, and step 2, you would run the problem, and both of those steps could be done in polynomial time. Then the whole problem can be solved in polynomial time. So what does that tell us? That this restricted version of the circuit satisfiability problem could not be in a class easier than the original problem, otherwise that other problem would move into that easy class too. Right? Whatever class the other problem was in, we could do these conversions in, this one takes no time, this one takes linear time, they all take linear time. We could run a linear time algorithm that takes the original problem and converts it into the format that this problem is looking for. We could do that in linear time. So step 1, convert the input, takes linear time. Step 2, use a solver for this problem to solve the original problem. If that could be done in less time than NP complete, that means the original problem was not NP complete in the first place. Because now someone came up with a better algorithm to solve that. So that original statement that the satisfiability problem was NP complete would then become a false statement. So if the original circuit satisfiability problem was NP complete, then this one must be also. So it looks like a much easier problem, but it's actually just, solving this one would be just as complicated. The only way to solve this one is try every input and make sure we solve the problem. Okay, so now, the thing that would take a while, it just takes a while to get used to these, but what we just kind of showed was, if the first problem, a random circuit, is this circuit satisfiable or not? That problem was considered NP complete. Actually, the hope was to show that it was exponential complete. Then we showed this circuit satisfiability problem where every circuit had exactly 3 inputs. They can't be random size, they had to be exactly 3 inputs. The gates all had to be OR gates. And then the OR gate results get ANDed together and you get your final answer. That sounded like a much easier problem because there's much more restrictions on it. But it turned out if someone could solve that problem, we would use that chart we just had before to convert our original problem into that problem and then solve that. So the solution for that 3 satisfiability problem is also NP complete. Now here's a random problem, but we're going to figure out a way to map this problem to the 3 conjunctive normal form problem. But here's the random problem. Suppose we had a graph, a collection of vertices and edges, and a particular number k, which is less than the vertices in the graph. Does the graph have a vertex cover of size k or less? That is there a subset of vertices in B such that all of the edges have at least one endpoint touching one of the vertices? So what that means is like this. If we had a graph like this, I'll use a simple example. We had a graph like this. We want to this has 4 vertices. We want to come up with a set of vertices, a subset of the vertices, so that we are touching every edge in the graph. So for example, this would not be a vertex cover because this edge is not covered, right? And then if we did a vertex, if we said, is this a vertex cover? Well, no, this would not be a vertex cover because this edge is not covered. This edge, both of its endpoints are not in the set. So if this was A, B, C, and D, A and D are not a vertex cover because there's an edge that's completely not touching anything in the set. Now, if we went like this, if we went like this, took all the points, that would be a vertex cover. Obviously, every edge would be covered. What we're looking for is, in this question, we're looking for you cannot use all the edges, you can only use K, and K is less than B. Some subset of the edges. Can we find, so we're given like kind of a budget we have to work within? So, for example, if we chose this point and this point, then we have every edge covered, right? These 3 edges are covered by this point. These 3 edges are covered by this point. This middle edge was covered twice, but that's okay. We just want to have a subset of the points so that every edge is touched by by at least one point in that subset. And then we have to do it in under K points. So I guess, yeah, your analogy you talked about before the class makes sense. I think you said you read online that a vertex cover would be like you're monitoring a bunch of hallways and you want to have a camera. I guess the camera can see 365 degrees and you want to know what's the minimum number of cameras you can put up to monitor all the hallways. So that's an example of a vertex cover. So then, so the edges are hallways and the vertexes are cameras that can see in 365 degrees. So you might think this problem, I shouldn't show this yet. You might think this problem is similar to the minimum spanning tree. It sounds a lot like the minimum spanning tree, right? A minimum spanning tree was you're given a graph and you're asked to come up with a subset of edges that covers every vertex. In this question, you're asked to come up with a set of vertices that cover every edge. So it sounds like the same problem, and we might be able to use something like Kruskal's algorithm or Prim's algorithm. But it turns out that this is a more difficult question. So The question is basically saying that we're going to make the statement that the vertex cover problem is actually NP complete. And the way we're going to make this point is, we already know now, we started off with the problem, the circuit satisfiability problem. We said that was NP complete. That was actually, if you do a look up on Google, that's the famous Cook's theorem. Cook's theorem was, which I think came out in 1971, circuit satisfiability is an NP complete problem. Then went on to show that the 3 literal version in conjunctive normal form is still NP complete. Even though it was it looks like a much easier problem to solve, it's still just as hard as the original problem. So now we're going to use that problem to solve the vertex cover problem. So here's the way we'll do it. We're going to take, okay, so for each literal A, we create 2 vertices. So here's the approach we're going to do. We're going to try to take a 3 conjunctive normal form problem and convert it into a graph. And then ask ourselves, can somebody come up with a solution for the vertex cover problem? If so, then we can solve the 3 conjunctive normal form problem. So we're going to take, for each literal A, we'll create a vertex A and not A, and then create an edge between them. For each 3 literal subclause, we'll create a triangle. 1 vertex for each of the 3 literals and 1 edge connecting the vertices to the node that, whether it's on or off. And I'll show a picture in a second. And then for each edge connecting each vertex in the triangle to the corresponding negative or positive or negative literal. So, let's say we had a graph like this. Let's say, so here's basically what we're doing. Let's assume somebody claims, I have solved the vertex cover problem. I have a polynomial algorithm that will give you the answer. Will give you the minimum vertex cover. So that's an algorithm we'll call vertex cover. We want to use that person's algorithm to solve the 3 conjunctive normal form problem. So for example, suppose we asked ourselves, is this 3 conjunctive normal form circuit, this is A and not C, I'm sorry, A or not C or not D, and not A or B or D, is this satisfiable or not? Well, we're going to create a graph from it. We're going to make a node called A and not A, B and not B, C and not C, D and not D, and put an edge between them. Then for every clause we have, so first of all we have 4 literals up here, therefore we have 4 of these links. Then for every clause we have, which have to have exactly 3 terms, because this is the special case of the 3 conjunctive normal forms, we'll create a triangle. And the triangle will go A, not C, and D. And we'll connect them all together. And then the next clause was not A, or B, or D. So we have not A, or B, or D. Then we make a connection. The final connection is we connect each of these letters to either the A or the not A up here. So, for example, this was an A, so we connect it to A. This was not C, so we connect this to not C. And this was not D, so we connect it to not D. And then the second one, since this was not A, we connected to here. B got connected to B, and not D got connected. This should be a D. Sorry about that. That should be D. D is connected to D. Okay, yeah, I got to change that slide. So now the question is, can you come up with a minimum vertex cover for this graph that is of size? Now, what would the minimum vertex cover have to be in this case? For a triangle, forget about everything else. For any triangle, what's the minimum number of vertices that have to be in the vertex cover? For a triangle? 2. There's no way you could have a triangle covered with one vertex, right? So you have a minimum of 2. So every triangle has to have at least 2 in the vertex cover. For every edge up here, the D and the not D, for this edge here, how many of these vertices would have to be part of the cover? At least 1. So now the question becomes, can we find a vertex cover of size 1, 2, 3, 4, 5, 6, 7, 8? 2 times the number of triangles plus 1 times the number of literals. Can we find a vertex cover of that size? And what would it mean if we could? If we could or we couldn't? If we could, then we're setting the inputs A, B, C, and D to either 1 or 0, but not both. And we're making the triangles become, we're making all of the triangles become true.
How do you, the triangles being true is,
Well, the
I'm not
triangles,
seeing that.
let's see, so if, oh, okay, so if,
Okay, I see.
if we set A to not true, then we don't have to worry about this edge, because we connected this one to here. So that gives us the freedom to assign we're kind of given a budget of 2 for every triangle. And actually, we're forced to use 2, otherwise we'll leave a triangle uncovered. So the fact that let's say I'm saying in my answer, A is, we're trying to satisfy the circuit, I'm saying A is false. If I set A to false, then I'm forced to leave this one uncovered. Because A being false means this A being true is not true. So if I say A equals false, then I was able to satisfy this circuit, I was able to satisfy this clause by making A false. So that gives me the freedom to cover these 2. So I can use up my budget. But this now forces this thing to have to be covered. Because if I'm saying A is false, then I have to use up one of my squares here. I get a budget of 2 per triangle. That's going to force me to leave one of these open, and the only way I could leave one open is connected to something I'm setting somewhere else. So basically what I'm doing is I'm being given a budget. What I'm doing is I'm taking this circuit, creating a corresponding graph, and then imposing a budget on myself of 2 per triangle and 1 per literal. And if I can cover the whole graph, then I can satisfy this circuit. And if I can't cover the graph, then I can't satisfy this circuit. So the way I'm satisfying it is as soon as I say, well, oh, this one ended up not mattering. As soon as I put this in my cover, I didn't need this to be true anymore, which means I could put 1 and 1 here. Now that these are covered, I now say to myself, as soon as I set not C to be true, that gives me the freedom to not have to cover this one, which means I can cover these 2. So it forces, the solution to the vertex cover of this graph, it's true or not true, is exactly the same as asking this question. So what now I'm doing is I'm trying to solve the original 3 conjunctive normal form problem by, instead of solving it in some straightforward way, I'm converting the input into a particular graph. And then hopefully someone will come along with a solution for the vertex cover problem that runs in, say, polynomial time. And now I've solved this problem in polynomial time. Right? So what I'm doing is, that's like the thing we were talking about before when we said, if somebody had a graph, I'm sorry, if somebody gave us a circuit, we would go like this. If somebody had a solution to the vertex cover problem, what we could do is we could transform the graph, transform the three conjunctive normal form problem into the vertex cover problem. This we could do in the number of literals and the number of three, this we could do in linear time. This first step, converting the input clause into that graph, we could do in linear time. Then somebody has some solver for the vertex cover. This whole box is now a solver for the three conjunctive normal form problem. Right? Step one, convert the input to a graph. Step two, run the solver for the vertex cover. What is the running time of this part plus this part? Well, it's linear plus whatever this is. But we know that this thing can never be solved in anything less than NP complete. So this whole big box is NP complete. It would be nice if it was exponential complete. If we said this box, out of all the algorithms in the world that will ever be invented, this takes a minimum of exponential time. If we were able to make that statement, what could you tell me about this solution? So if this out of box, solving the three conjunctive normal form problem, the three conjunctive normal form stat problem, this takes a minimum of exponential time. This also would solve the problem. Step one, convert this problem into a graph, and then step two, run the solver for this.